Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at the quality of our Lewis structures by using formal charges. So this is a way to try and evaluate the stability of a structure just by seeing where the electrons are on the system and are they on the atoms that they want to be. So a good way to think about this is formal charge is another way of just looking at, does an atom have too many electrons or too few electrons? And in general, atoms want to minimize their charge, whether it's negative or positive. And so we're going to try and evaluate the charge on each atom, in this case, by looking at the number of valence electrons on the atom. So we'll go ahead and look what group each element belongs to. Carbon should have 4, nitrogen 5, oxygen 6. And then we're going to subtract out the number of electrons actually on the atom. That way, if the system has too many electrons, we should have a negative formal charge. And if it has too few, we should have a positive formal charge. Now, how do we actually evaluate how many electrons are on the atom? So here we're going to make use of a combination of lone pairs and bonds. So a good way to think about it is that if I've got a lone pair, that electron is always on the relevant atom. However, if I have a bond, I've got 2 electrons that are each on the atom about 50% of the time. So we're going to count each bond as more or less a single electron. This is also known as just taking half the number of electrons on the bond. So the sum of our formal charges, we can then use this to figure out a formal charge of each atom, and the sum of formal charges on the molecule should be equal to the overall charge of the molecule. So if I have a molecule that has a -1 charge, when I add all my formal charges together, I should have -1. So let's go ahead and take a look at what this looks like for a real sort of structure. So let's go ahead and take a look at our acetate molecule that we built last time. So this way, so when we're evaluating formal charges, we have to look at each atom individually. And generally, the easiest place to start is our hydrogen atoms. So each of the hydrogen atoms has 1 valence electron, and each of them have a single bond. So we can take the number of valence electrons minus the number of bonds. And in this case, all of our hydrogen atoms have 0 formal charge. So that's good because remember, atoms like minimizing formal charge. Now, you'll notice that we have a slightly different bonding network for each of our 4 heteroatoms, so carbon and oxygen. So let's take a look at carbon 1. Carbon has 4 valence electrons, and this carbon has 4 bonds, so it should have a formal charge of 0. This carbon atom has 4 valence electrons and 1, 2, 3, 4 bonds. Again, this time 2 single, 1 double. So it also has a 0 formal charge. Now let's go ahead and look at oxygen 1. Oxygen has 6 valence electrons. This oxygen has 4 valence electrons, 1, 2, 3, 4, and 2 bonds, 1, 2. So this gives us a 0 formal charge. So far we're looking very good. Now let's take a look at our lost oxygen atom. So all oxygen atoms, 6 valence electrons. This case, we have 6 lone pair electrons and 1 bond. So I have a -1 formal charge. So not necessarily great, but remember, our acetate has an overall -1 charge. And so somebody has to bear that -1 charge. In this case, it's the oxygen atom. So all of our formal charges added together gives us the overall charge of the molecule. So this is looking pretty good. But is that -1 formal charge in the most stable place? And so for this, we can go ahead and use some rules for evaluating our stability using these formal charges. So the first thing we want to do is try and minimize the number and magnitude of formal charges. So our last structure, we only had 1 atom that had a formal charge, and somebody had to have a -1 formal charge. So we're doing pretty good. 2, make sure that the negative charges appear on the most electronegative atoms. So oxygen is our most electronegative element, so we're pretty good. Occasionally, you'll have a positive formal charge appear, and you're going to want to tend to put them on the most positive electropositive elements. So a metal, if you have it, And if you're dealing with nonmetals, typically this will be something like carbon. And again, one of the biggest things is elements with negative formal charges don't want to be near other elements with negative formal charges. Elements with positive formal charges don't want to be near other elements with positive formal charges. You're going to want to try and keep your charges separated. If you have an element with a negative charge, it will typically want to be near an element with a positive formal charge to kind of help cancel things out. Now, let's go ahead and take a look at some of the other potential structures, one of the other potential structures we generated for acetate. So in this system, we put our oxygen atoms on different carbon atoms. And let's see what this guy looks like. So in this case, carbon 1 has 4 bonds, so it has a 0 formal charge. Carbon 2 has 3 bonds and a lone pair. So this gives us 5 electrons and a -1 formal charge. Oxygen 1, 2 bonds and 2 lone pairs for 6 electrons, so 0 formal charge. And oxygen 2, 2 bonds, 2 lone pairs, 0 formal charge. And hydrogen atoms all doing fine. So in this case, while we have minimized the number and magnitude of formal charges, we failed here on the second point because oxygen is more electronegative than carbon. So the system would much prefer that negative charge to be on oxygen rather than carbon. So while this structure does technically work, it isn't going to be nearly as favorable as our last one. So again, good thing to try and remember, if you have to give extra electrons to somebody, put it on the oxygen. Now, one of the things we'll occasionally find is that a Lewis structure, a real structure can be represented by more than a single Lewis structure. As again, we have with this acetate case, because we have 2 very similar Lewis structures. They only differ by the position of a double bond. And if we have 2 structures that again share the same skeleton structure, but the only difference is electron or bond position. So essentially the electrons can move around to put double bonds in different locations. They can form what we call resonance structures. And a good way to think about resonance structures is that all of our electrons tend to move very quickly. And electrons, being quantum mechanical in nature, like to spread out. So in truth, what we have is a system where both of these Lewis structures are true. And that the electrons are going to probably spend about half the time in one structure and half the time in another structure. Now, if one of these structures has more stable formal charges than another, we'd expect the one with the more stable formal charges to be the one that the electrons are going to spend more of the time in. However, that doesn't mean that the other one is technically impossible and never occurs. It's just much less likely. And again, this only holds if they share the same skeleton structure and there's a way to rearrange the electrons. So this gives us a way to evaluate stability of systems. However, there's still a couple nuances of Lewis structures we have to hit on. Most notably, it turns out not every atom has to obey the octet rule. So next time, we'll look into which atoms don't play by the rules. Until then, take care.